This is an example of an AC analysis problem on level 1. So AC analysis is a tutorial that covers many aspects of AC or phasor analysis of circuits in the phasor domain using techniques such as voltage and current division, superposition, source transformation, and Thevenin and Norton equivalent circuits. So everything basically other than nodal and mesh solution, which are covered in other tutorials here. So we'll enter the AC analysis, and I'm going to select a particular problem type within level 1 here. Now, as always, we do have examples available at different levels of difficulty, and it's always a good idea to look at that. So let's just look briefly at an easy example of this type. So this is a problem with a single loop circuit, as you notice, and when we have voltage sources in series like that, we can combine those voltage sources by adding their values. Now these values, because we're in the phasor domain here, this whole problem you can tell immediately is given to us in the phasor domain because the impedance of the reactive element is a complex number and in units of ohms rather than being in farads as it would be in the time domain. Further, instead of the voltage being given as a function of time, as a cosine function with a magnitude and a phase, we see it's being given to us in the phasor domain. So this is a complex number in polar form with the magnitude and the angle here. And we are told the frequency, although we won't really need that until the very end of the problem, the angular time frequency here, omega. So that's just a matter of combining those two things in series by adding those two complex numbers together, which would be done on a calculator, as is illustrated here, the result. And that then gives us a simplified form in which we now have a simple voltage divider because we have two impedances in series with a voltage source. So then we can use the normal voltage divider formula, the same formula that we would use in a DC circuit. So we have the voltage of the source, and we might need a minus sign there, but we check that the plus sign is connected to plus here, negative to negative there. So in fact, there'll be a plus sign in front of that. So this is phase angle of the source, as opposed to, for example, if you wanted to put a minus sign, you could, in this case, probably subtract 180 degrees from this phase angle. It would be the same as putting a minus sign there. And then it has the impedance with the sought voltage, the 9 ohm, divided by the sum of that and the other impedance, which is negative J4. And then this expression is simply evaluated on a calculator to give us this value in the polar form, as you notice. And then that's converted by doing an inverse phasor transform into the time domain. So the corresponding voltage in the time domain then, which is a function of time, would be this magnitude times a cosine function of the angular time frequency, which, as we were told, was 0.6 kiloradians per second, or 600 radians per second, minus 180 degrees, because that's the phase angle, and that would be in units of volts, just as the phasor is. Both the time domain and the phasor have to have the same units. So that's just an example. But now let's work through an actual problem here of the same type. So when working the problem, we're being advised that it would be a good idea to first simplify the circuit, which we can see is true because we can't use a voltage divider formula unless we have a single voltage source. And it is a single loop circuit, we can see that. So instead of analyzing it, I mean, we could analyze this just by writing a KVL equation for the entire loop. So that's one option, but it's probably a little bit easier to combine the voltage sources. So I'm going to do that. And it does gives us some written instructions here on how to do simplifications. And so you can scroll through that. There's a lot of detail there. So I'm going to now try to simplify this. I can't combine those two impedances in series. And notice, as I said, we are in the phasor domain because these are in ohms. Or the inductor values in ohms rather, and the voltages are written as complex numbers, which for sure indicates that we are in the phasor domain. So normally you could combine two impedances in series, but one of them has a sought voltage here. And so, we could do that if we wanted to make a sought variable transformation, But instead, let's just use the voltage divider formula, and then we won't need to combine those. So what we will do is to combine these two sources. So in doing that, we have to notice how do their polarities compare. Well, if we go clockwise, for example, we reach the negative sign of this one first, and then also reach the negative sign of this one first. So that means that they basically both have the same polarity. Or another way of saying that is that if this were the only source, it would make current flow, at least nominally. Of course, it's really AC, so it goes back and forth. But ignoring that, it would normally go from plus to minus, so it would go clockwise. Whereas this one also would make the current flow through the external circuit from plus to minus. So in other words, it would also go clockwise. So those voltage sources, in fact, add rather than subtract. So we need to add those two numbers together to get the resultant voltage source. So let's do that math. We basically, 4 angle 0, we can just think of that as 4 really. 4 plus 1 angle 150 degrees. So we're going to do that on the calculator here. Now, just remind you that in order to do any calculations with complex numbers, it's vital to make sure that we are in a complex mode. Otherwise, it will not give you any correct answer at all. So we go into mode on the calculator, and by default, you would be in this real mode down here. This would be highlighted, in which case it's not going to work. So I've already actually put it in the rectangular mode, but for this problem, I think I want to have it in the polar mode, so I'm going to go down there. And this really just affects the way things are displayed. We can enter things in either mode. So we're going to do that, and then press enter to set that. Now, for my particular calculator here, and for this emulator, it will actually not work correctly if I try to do things initially in the degree mode. In some models of these TI 83, 84, or maybe some software updates, I'm not sure, it will work, but in this case it will not. So I'm going to go up here and set this into radian mode initially. So I'm going to push enter there. And now that I've set my modes appropriately, I can push clear to get out of that. Now, in order to do calculations easily, I'm going to define a variable e, which is going to be e to the I pi divided by 180. And that's because on this model, the TI 83 or 84, even though I may be in a degree mode, for example, if I did change it into degree mode, it always interprets the arguments of a complex exponential in radians. And so you have to convert them to radians. That's rather inconvenient. That's not true on a TI 89. There, the mode setting will control how those numbers are interpreted. But in this calculator, it does not work that way, which is a rather odd feature that this calculator has. So what I'm going to do is I'm going to define a value. So I'm going to write an expression, which will be e. So I go second logarithm, which is e to the x. And now I'm going to enter an I times a pi, so second pi here, divided by 180, which is degrees. Now if I multiply this by a number in degrees, or equivalently raise this whole thing to a number in degrees, that will automatically, the pi over 180 will convert that into radians so that I'll get the correct answer. So having defined that, I'm basically going to store that entire expression. Well, I need to go, I guess, out of the expression first. I'm going to store that in a variable I'm going to call e. So I go alpha e here to put it in that variable, and then enter. And that's now displaying in radians the value of that. So now I want to go into degree mode. So I'm going to change my mode now. And I can't do it initially. I have to do this first calculation in radian mode or it won't work. So I'm going to go now mode into degrees. And so I have to go down here and over to degrees and enter that. So now I'm in degree mode. And now I'll test that by going E, that variable I just created, raise that to a power, and for example, suppose I use 45 degrees. Well, what that really does is take little e to the I times pi over 180 times 45. So in other words, it's e to the I theta, where theta is 45 degrees. So let's see what that gives me. Okay, in radian mode, it gives me that. But let's put it, just for testing purposes, I'll change that mode to rectangular mode, just so that I can see if it's correct. And well, I have to go up here and then enter that. Okay, so that did not work. So, oh, I selected the wrong thing. So what I meant to do was to go up and select this again, or I could have just used answer actually. So I'll enter that. There we go. So now we have basically, if you think about an angle of 45 degrees on the unit circle, that should give you square root of 2 over 2 plus the square root of 2 over 2 times I, or j. And that square root of 2 over 2, square root of 2, remember, is about 1.41, so square root of 2 over 2 is about 0.707 plus I times 0.707. So that checks that this is working correctly. So now I can use that to enter numbers. So now I'm going to clear all that and just do the actual calculation that I need here. So I need 4, and I don't really need to put the angle there since it's just basically a real number if it has an angle 0 degrees, plus 1 angle 150, so I'm going to go 1. And I could put it times, although I don't really need to do that. And then I'm going to take that variable e that I defined and raise that to 150 degrees and enter that expression. And there it is in rectangular form. However, I actually wanted that in polar form, so I'm going to change my mode. I could use a function, but I'll just change my mode back to radian, or I'm sorry, back to polar form. So I go down here and select that. And now I can just take select that and go enter that, and that will now be in polar form. And now this is in degrees, remember, because I've selected the degree mode. Let me just double check that to make sure. Yes, I am in degree mode, so that's good. Okay, so that is 3.17 angle 9.065 degrees. So let's put that in as a value, and we can pick either source. It doesn't really matter. So I'm going to put 3.174, putting that into 4 decimal places, and then the angle here is going to be 9.065 degrees. And then this source, we will change it to a short. And now I'll check that combination of sources. And that is correct. Okay, so we've done our calculation correctly. So now, let's see. Oh, there's the dialog box got moved over there. That was not full screen. Let's see here. I have to scroll over and get that. Well, it doesn't want to come back where it's supposed to be. Okay, so I'm done editing, so I'll click that. And now I want to write the analysis using single loop analysis, because I have a single loop in my circuit. I do not have a single node pair. So I select single loop, and I want to use basically a sought branch voltage, so I can use the voltage divider formula directly. So I select that, and now I have V naught is going to be equal to, and I'm going to use this formula, which takes the voltage of the source times one impedance divided by the sum of the impedances. So that's the formula that I will need. And so now the source value is that 3.17, angle 9.07, and you'll probably have that displayed to 4 digits, so it would be better to use 4 just for accuracy. And then the impedance of interest across which this V0 drops is 2 ohms. So I'll enter 2 there, and then this will be 2, and then the other one will be the J7 ohms. So that's the basic voltage divider formula. Remember, you always have essentially the voltage source divided by the total impedance is the current flowing in the circuit, and if you multiply the current times the resistor of interest, that will give us the voltage drop across that resistor of interest. That's the rationale behind the voltage divider formula. Now, we do need to be very careful about polarity as always. So let's observe that the plus sign of this voltage source is actually connected to the negative side of this voltage, and its minus side is connected to the plus side. That means this has the opposite sense as this does. So we can either put a minus sign here, which I'll do, or we could subtract 180 degrees from this, or you could also add, although usually we want it in the range of negative 180 to 180. So I think that would not actually be accepted there if you add. So that would be another way of doing it, or we can just let the computer do it for us by putting a minus sign here. So now we'll check that equation, and that is correct. And that's the only equation we need here to get V0, so we're done. And now we need to enter a numerical value for this. In other words, just evaluate this expression and put in a number in polar form. So once again, we'll need our calculator. So now we're going to have negative and I'll put parentheses here just to be on the safe side. So we have 3.17. And I don't really need the times, but I'll use it times E. And remember, I need to use that variable since I want to put my angle in degrees. Engineers usually work in degrees rather than radians, so it's convenient to be able to work in degrees. So we have that E raised to the power. And don't forget that power. If you multiply by E, then you'll get a drastically wrong answer, and it won't be correct at all. So we have to raise that to a power, and that's going to be 9.07 degrees. So we put 9.07. And then we close our parentheses there. And I suppose, I'm not sure if we needed parentheses there, but I'll just put them in to be safe. Now multiply that times the 2. And then divide by that sum of 2 plus I times 7. Notice that we can have some numbers here in polar format and others in rectangular format. It doesn't matter. The calculator doesn't care, and it will do all the conversions that are necessary for you automatically. That's why you always want to use a calculator that is capable of handling complex numbers directly, as we're doing here. So now all we have to do is press enter, and that does that in one step. If you're doing multiple steps, you're probably not making proper use of the functions of your calculator. And you certainly don't want to be using inverse tangents or square roots or things like that to do complex numbers, because that would take much longer, and this is a much more efficient way of doing it, to use the properties of a calculator basically directly, or the capabilities rather. So now we'll enter that value. So we have 0.807, or I'm sorry, 0.8709 rather. And then the angle, again, this is in degrees since I've used the degree setting. And remember, you always have to know what mode, and it shows that up here. It shows you're in degree setting. Also, you see that this indicator here on the top of the screen in your display shows that you're in polar mode. Now, if it said real, then none of this is going to work. So you have to make sure that you're in the proper mode. Okay, so that would be 115.0, or just 115 will do. And we'll check that. And that is correct. And then the final step here is to put the sought voltage into the time domain to do an inverse phasor transform. So basically we just look at this value, and the magnitude of the complex number becomes the magnitude of the cosine. That becomes the amplitude. And our omega multiplies t. So remember that omega was 3 kiloradian per second. So we're going to enter that just as a number. So we'll write 3,000. And the angle then would be that 9.07 degrees. And I don't think it accepts the metric prefixes here, so we'll just write that as 3,000. And we'll check that. Oops. Let's see. Oh, I was reading the wrong number. I'm sorry. I read this value when I was supposed to be reading this value. Okay, so, and notice that when you do make a mistake, it will color both the amplitude or the magnitude and the phase angle wrong. It doesn't mean that they're both necessarily wrong, but one could sort of affect the other, so it colors both of them. So that should have been 115 there is what I meant to enter. And that is correct. And that concludes this problem.